Okay, so it's a pleasure for us to have today Stechmann from the University of Wisconsin-Madison. So Sam is a professor in mathematics. So he has got a PhD in mathematics at the Courant Institute at New York University, and then made postdocs at UCLA. And he's a specialist of applied and computational mathematics, mainly applied to atmospheric science and climate. So he uses computational mathematics, PDE, stochastic processes, and he worked a lot on tropical weather and climate, clouds and convection. So today he will speak about some very interesting work in order to better understand moist dynamics at a fundamental level. So Sam, I let you go.
Yeah, there we go. Good. Thank you very much. Thanks a lot for the invitation. And as Freddie was saying, this is work toward adding clouds to some fundamentals of GFD. And before getting into the details of that, I work a lot on clouds and rainfall, and so I think it's worthwhile asking, why spend so much time on clouds and rainfall? And it's partly just because it's pictures of clouds, and looking at real clouds is just beautiful and intriguing. But it's also some of the most important topics for society. So clouds are the leading source of uncertainty in climate predictions, and this is because of their impact on radiation. Clouds can reflect incoming solar radiation back to space, which can have a cooling effect on Earth, and clouds can also absorb outgoing long-wave radiation from the Earth's surface and re-radiate it and have a warming impact. And different types of clouds can have different impacts. And so these are uncertain effects that we need to understand better. And on shorter timescales, rainfall is arguably the most difficult quantity to predict in weather forecasts. And this is a plot that just illustrates that the forecast scale of temperature versus precipitation. Although you are probably familiar with this from your everyday life, that the weather forecasts for temperature are far superior than those for precipitation. So these are a couple of examples of why we need improved understanding to help with this. And we need more than just improved understanding. I mean, certainly there's other aspects like observational uncertainties and issues with modeling and simulation, but there's also pretty big gaps in our theoretical understanding of things too. Oh yeah, and I was just checking the chat. Yeah, so please feel free to ask any questions at any time. Okay, and so there have been a variety of different types of theoretical advances related to clouds and fluid dynamics of clouds. And so I wanted to put this talk in context of other work too. So there have been advances related to rigorous proofs and PDE analysis. There have been asymptotic models. There have been various types of simplified models for trying to understand clouds better, advances in our understanding of thermodynamics. And I'm only listing a small subset of examples of all these. There's many other more contributions. And so, and then there's this other category, which is what I'll talk about today, where I'm trying to think about principles of geophysical fluid dynamics and try to think about cloudy versions of them. And so to say a little more about that, if you think about dry dynamics without moisture, this is textbook material, and here's a few of my favorite books from my shelf. And on the other hand, when you think about moist or cloudy geophysical fluid dynamics, there's a lot less known, and it's because of the complications of clouds and precipitation. So here today, I'm going to talk about work towards defining some of these fundamental principles with clouds, and I'll talk about three aspects. First, energy, and then potential vorticity, and the quasi-geostrophic limit. I'm trying to think about those if we have clouds present. Okay, so first off, energy. And so what we have for energy is a new version of the energy with phase changes, with clouds. And it has a really cool form. It's piecewise. Well, I guess I'm giving that away right away. It's going to be piecewise quadratic. So there's kind of two ways of writing the energy that are both pretty useful. There's a rho gz version of the energy. So in the dry case, the potential energy is rho gz, or buoyancy times height. On the other hand, there's quadratic versions of the energy that you could write down, where the potential energy is the buoyancy squared, and divided by the Brunt-by-Sola frequency squared. And both of these are useful for different reasons. Obviously, rho GZ has this nice physical intuition that goes along with it. The quadratic energy is useful for other things, like it defines a norm, and you could possibly relate it to an inner product. And when you ask, well, what do we know about energies for the moist case, if I have clouds and phase changes? This is one version that had been written down in the past. And it's an extension of the rho GZ-like energy. Instead of multiplying by Z, it's really supposed to be an integral with respect to Z of the buoyancy. And so what we were asking then is there a moist analog with clouds or phase changes of this quadratic energy, which I'm calling E2 here? And the answer is yes. And we found that it takes this form down here. So now there's three pieces of potential energy here, which I'll talk about in a minute. And this was work with Leslie Smith and a former PhD student, Dave Marsico. And so kind of the interesting pieces here are there's a buoyancy squared term, kind of like in the dry case, and the U and the S represent the different phases, unsaturated phase, and so where there's no cloud, and the saturated phase where there is cloud. And these H's are heavisides that are indicating these different phases. And then there's this third piece. So these first two maybe would not be too surprising. Maybe the more interesting one is this third piece is with this M squared. And so this M squared is the differences. It's a weighted difference between the buoyancies. And you can define it in another way too, that'll come up later. And this quantity is material invariant. And so this piece, it's related to moisture, as I'll explain later, and you can view it as a latent energy, a moist latent energy. And I'll try to get to this a little later. And the reason it comes up is because there's more variables, and there's another eigenmode in the system. So over the next few slides, I'll try to say a little bit more about where does this come from, and what do these different terms mean. And so first off, I guess I should say what system am I talking about? So this is an energy that is conserved for the moist Boussinesq equations with phase changes. And I view this as a great system for GFD type purposes. It has the basic ingredients of the phase changes and the clouds, but it's also, the thermodynamics is a little simpler. And so it's an easier system to work with. So I will use this as an example throughout this talk. It also can be viewed as a good building block or a foundation for trying more complicated cases with more complicated microphysics, or getting into inelastic or compressible dynamics. So we have our momentum equation with pressure gradient and buoyancy, and it's Boussinesq, so it's considered incompressible. And then we have the thermodynamic equation. So if these were just the dry equations, then we would stop here with our potential temperature theta. There would be no source term. For clouds, this C represents the condensation and evaporation. But we are thinking about clouds here, and so we include two additional equations, one for the water vapor and one for the liquid water. The tildes here are the background or reference states. And so the theta and the QV, these are anomalies from the reference states. And this C for condensation and evaporation, I'm not going to go into too much detail about how it's done, but in the precise definition is down here, and it's more or less defined just to maintain the constraint that the vapor is not allowed to go above saturation. So the vapor can be below it, but as soon as it hits the saturation value, this condensation or evaporation will turn on in order to if you go above saturation, then you have to condense water to turn into liquid. So there's a loss of vapor, a gain of liquid, and corresponding to that, there's a heat source here in the evolution equation for theta. Okay, and so this question down here is related to, you might be wondering, I write these equations down and they probably don't look much at all like this version of the energy I wrote where there's these buoyancy variables and this M coming up. So what I want to do over the next few slides is show how we can rewrite the system of equations in a way that makes it easier to identify an energy that's conserved for the system. Okay, so the first step.
So, excuse me, Sam. So the d over dt is the convective derivative, I guess. Is it what is the? Is it horizontal convection only or vertical convection?
Three-dimensional. Yes, I'm sorry. I should have put that. Yes, yep. The three-dimensional material derivative, the partial ddt and the u dot grad. Yep. Thank you.
Thank you.
Okay, so the first step is to use a different set of variables, which is gonna make things easier. So rather than using potential temperature, water vapor, and liquid water, we're gonna change to conserved variables, equivalent potential temperature theta E, and a total water QT. So we had these three evolution equations from the last slide, and now we define these new variables like this right here. And I'll start with the total water because it's a little easier. The total water is, as you might expect, it's add up the vapor and the liquid and you get the total. And it has an evolution equation like this down here with a 0 on the right-hand side, because if I added the vapor and liquid evolution equations, the condensation evaporation terms cancel, because when you have clouds, you are just converting water from one form to another, from vapor to liquid. You're not changing the total amount that's there. And so that's why this is a conserved quantity. Theta E comes up from a different combination. If I add together the potential temperature and the vapor with a certain weighting factor related to the latent heat, then these C's on the right-hand side will also cancel, and I'll get another conserved quantity. And physically, what is going on here is that this is conserved because if a cloud forms and I lose vapor, I also gain heat because the phase change is associated with heating. And so this quantity theta E will remain conserved. And this version of it, this is one of the reasons I kind of like this Booth-esque framework where thermodynamics are kind of linearized. If you look in a thermodynamics textbook, you'll see a much more complicated formula for this. And so this is sort of a building block for thinking about things in a simple setting, but you can use a lot of these ideas with more comprehensive systems too.
Sorry, Sam,
okay,
could I interrupt you a second? There's a couple of questions in the chat which I think are quite important. So
okay.
We have a question about what the tilde means over the, there's a tilde over the theta and over the QV.
Yes. Yeah, the two tildes, these are reference states. So I'm taking the total water back reference state to be the same as the vapor in creating these. And I see there was a question about the pressure too. Sorry. Yeah, this P, it's a scaled pressure, so it's scaled by a reference density. So the units, the units don't look precise. It's right here. And was there another one? Can supersaturation be accommodated? So I'll mention some additional cases in what's coming up later. So in the particular form of the energy that I wrote down, it's for this system with 0 supersaturation. I don't think I've written the equations down in the case where supersaturation is allowed. We've explored a little bit the case of Kessler microphysics, which I guess has supersaturation. So I guess what I mean is I don't know if there's a beautiful statement of energy conservation when there is supersaturation. And so I like this case because you get this really nice looking quadratic, piecewise quadratic energy if you don't have a supersaturation. You can write down energy statements, although I don't remember them off the top of my head when you start adding in the extra pieces, and you won't get a nice, I don't think you'll get a nice conserved quantity, but I'd have to look back at what we did for the Kessler case and to think about whether you could do something with supersaturation here. even without rain. But yeah, that's a good question. Was there another one? Do we take into account reduction of buoyancy due to condensate loading? Oh, okay. So yeah, another thing, you'll notice that my buoyancy, I'm just writing it as theta. And so I'm partly doing this just for presentation. It's the easiest version to talk about. But yeah, you could add in contributions from vapor and liquid and other things here to use more complicated formulas. If you make that change, it does not have an impact. You would still be able to get a piecewise quadratic version of the energy. It's just your definitions of these buoyancy variables would change a little bit. Yeah. Oh, lots of good questions. Okay. Okay, so now with these new variables, so we said we removed the right-hand sides, this condensation term, but there must be something still here, right? It's not like we just totally got rid of clouds and they're gone. So the piece that's remaining is the buoyancy. So that in this simple version of the buoyancy, where it's just theta, we now have to write theta in terms of our new variables, theta E and QT. And so there's just formulas that you can write down, and it's a different formula depending on which phase you're in. And so this is where the heavy sides come in to indicate which formula I should be using. And so the heavy side is just, it equals 1 if our total water is above saturation, and it's 0 if it's below saturation. Okay, and from here, there's just one more step, and it's to get the system in terms of these buoyancy variables. So that expression we had for theta on the previous slide, I can just define this as a new variable. I'll call it BU for the unsaturated buoyancy and BS for the saturated buoyancy. And then my buoyancy takes this form right here with the heavy sides explicit, and I can write the evolution equations for these quantities BU and BS by just using the evolution equations for theta E and QT, for instance. And so now the system takes this really nice form, and it looks very much like the dry system now. So if I just had HU equal to 1 all the time, then I don't have any clouds, and I have this BU variable is like my usual dry buoyancy. And so now you can see maybe where that version, if I go all the way back, where this version of the energy comes from. It's because this looks exactly like the quadratic dry energy if I were in this unsaturated phase, and this looks like the quadratic energy if I were cloudy everywhere. And then the tricky piece is this m squared part of the energy. And I need to get this thing out of my way so I can go to the next slide. Okay. The menu bar popped down. Yeah, so then there's the third piece is the m, and so I guess I should go back and show that again. So the definition of it is this weighted difference between the buoyancies, and that's to try to get rid of, to try to get a material invariance without this extra term. So if I add these two in the right weights or subtract them with the right weights, then I can get these W terms to go away. So this, going back now, this extra piece in the energy, if I didn't have this heavy side, then this would just be conserved and have no impact. So the role of this moist energy is it's latent energy and it's sitting around, and it's there in the unsaturated phase. And when I change to the saturated phase, I have to make up the difference in potential energies, because the Brunn-Fiesola frequency is lower when you're in the saturated phase. And so since this is smaller, the potential energy is greater when you're in the saturated phase. And so where it comes from is this new potential energy you have in the saturated phase. It's actually the sum of the old dry potential energy and then this latent energy, this latent moist energy that was sitting around. And to make that explicit, I can write out I think that's what's next year. I can write out the energy transfers. So if I write the evolution equations for each of these 4 pieces of the energy, the kinetic energy has these terms from the buoyancy, and it's split into 2 pieces now, depending on what phase we're in. And the potential energies are contributing to those transfers with kinetic energy. And this moist energy, it has a contribution only at the phase interface. So I'm writing these as derivatives of heavy side. So they're basically Dirac deltas right at the phase interface. And so this is what I was saying a minute ago, that the moist energy is related to the exchange between potential energy in the two phases. So the moist energy is sitting around and waiting for its opportunity. When the cloud forms, then you lose the moist energy, and it is gained by the dry potential, or sorry, the saturated potential energy here. And so this has this nice physical interpretation that when there's a phase change, the latent moist energy becomes available. It's kind of interesting that this is different from the traditional viewpoint. You can write an energy down with the latent heating, like LV, QV. And so this is a little bit of a different perspective, and we're still working to try to make that comparison really precise, so you can compare what this means, this type of energy versus that traditional one. Another little note about this. So I said right away at the beginning that there's kind of two ways of writing the energy. One is this rho GZ like version, and the piecewise quadratic. It turns out that they're the same, which they probably should be, right? Or they're the same up to a difference between them that happens to be a material invariant. This is a bit of a calculation that's tucked away in the paper in the appendix or SI or something, but you can show that they are indeed the same. You just have to evaluate this integral. And so, yeah, I was mentioning this earlier that we use this Booz-Ness case because it's a good foundation. It kind of contains the simplest version of phase changes in clouds, but you could add in lots of other complications. You can make the buoyancy more complicated. You can try this for the inelastic equations. We found a similar decomposition into like unsaturated, saturated potential energy, and then this moist latent energy. Although for the inelastic case, it's not a quadratic energy anymore. We were able to add precipitation and to get a really cool conserved quantity in that case if we used a really simple version of microphysics, which is based on having fast autoconversion and rain evaporation. And we've thought a little bit about the Kessler case, but it's not as pretty and clean. And one thing we're working on right now is the compressible case. And this will be the case where we can try to make a better connection with the LV, QV type of latent energy that is most familiar to people. And there's lots of other cases that you could add complications to. And so just to put this energy on the screen again, it's piecewise quadratic. It has this cool latent energy with m squared. And looking back, I feel like the keys to finding this were writing the equations in terms of the conserved variables and the heavy sides. And this m variable came up, and it'll come up again in this talk. I feel like this is an interesting new piece of the puzzle with cloudy fluid dynamics. Okay, and so after having found this, we start thinking about, well, what can I use it for? And so a first application that comes to mind is principal component analysis, or EOF. And so this is an example where we ran a large eddy simulation of non-precipitating clouds, boundary layer clouds, and we want to compare the EOFs under a couple different cases. So one is, what if I just used a standard L2 energy for the principal component analysis? So if I take one of these buoyancy variables, so basically taking like theta or theta L as the quantity, versus what if I use a piecewise defined energy where I give a different coefficient depending on which phase I'm in. And so when you do that, your leading EOFs in these two cases are very different. The leading EOFs in the standard L2 energy case, they don't really capture the entire cloud layer. If you move in and take into account the different phases in your definition of the energy, then the leading EOF has this structure that goes deep, and this is roughly through the depth of the shallow cloud layer. And so we think this could be useful for trying to analyze cloud data in different ways, since using the natural moist energy does a better job of thinking about the variability of clouds. And as a second application, when you have an energy, you could start thinking, can I could I also use this quantity as a Lagrangian or a Hamiltonian? And so that actually brings us now to this second part here on potential vorticity. Okay, and so potential vorticity, as you know from the dry case, it is conserved, and it's defined like this, as vorticity dotted into the gradient of potential temperature, and it's a material invariant, and this goes way back. This is one of the fundamental conserved quantities of GFD, if not the fundamental one, in encapsulating stratification and rotation. And it goes way back to Rossby and Ertel. And there's been a question, is there a definition of PV that would be conserved when you have clouds? And you can try. Past approaches have been to, well, let's maybe try to guess what might be the right extension. And so maybe I need to replace this potential temperature by something that includes moisture, like virtual potential temperature or equivalent potential temperature. But when you try these things, you'll discover that they're not conserved. And so our approach now is going to be to take a systematic approach. And we can do this now that we have this conserved energy. And so the systematic approach is to think about Noether's theorem. So Noether's theorem says that if you have a conservation law, then it's related to a symmetry in the Lagrangian. So a systematic approach to thinking about PV conservation would be look at your Lagrangian and try to see what symmetries it has. And so just to review, Lagrangian in most cases is kinetic minus potential energy. And Noether's theorem, some other examples of this that you're maybe familiar with are conservation of momentum. And this happens when the potential energy is the differences between particle locations, for instance, because then you could translate the entire system spatially and it would have no change to the potential energy in the system. Or another example is conservation of angular momentum, which as one example can arise when your potential energy depends only on the magnitude of position. So you could rotate your coordinate system and it would have no change to the potential energy or the Lagrangian. Okay, so now for PV, this you may or may not be familiar. This is in some GFD books, but not all. Like this is in Salmon's GFD book, for instance. Conservation of potential vorticity is associated with what's called the particle relabeling symmetry. Okay, and so just to review this in the dry case very briefly, every particle or parcel in the system could be given a label, and it's often called vector A. So as an easy example, let the initial position of the particle be its label. That's a unique label for every particle. And now the symmetry is that I could relabel the particles without changing the Lagrangian or the potential energy. And in the dry case, my potential energy is the internal energy, thermodynamic internal energy. And you could include the gravitational energy into this too, but really the key part for the discussion is the internal energy, the potential energy. So in this case, you could write it as a function of the density and potential temperature. And what you find is that I can relabel the particles and keep this potential energy the same if I make sure to keep their theta values the same. So this means that I have sheets, I have surfaces of constant potential temperature, and I can do my particle relabeling within each one of these sheets or surfaces. And the conservation law that you get out of this is the Kelvin or Kelvin-Bjerknes circulation theorem on a surface of constant theta. And these go way back to a couple of centuries ago. And you can take this another step by using Stokes' theorem, and you can get to the PV conservation law. And so you could, from a simple viewpoint, you could say that this PV defined with grad theta that comes from having Kelvin-Bjerknes circulation theorem and the potential energy with theta here. Okay, so now we want to try to do this with clouds. And so the question is there a particle relabeling symmetry? And the answer could be no. It could be that there is no symmetry of the Lagrangian anymore. And maybe that's why we've never been able to come up with a definition of conserved PV. Or maybe there is. So let's try to think about this now. So, and I'm not even going to write down, we did use the energy from before when we were doing our research on this and trying to figure it out, but I can tell you the basic ideas by just describing it in this way. I have a potential energy, which now depends not just on theta, but it depends on theta E and QT. And so what this means is that if I'm going to have a symmetry, if I'm going to keep this potential energy the same, I can relabel my particles, but now I have to keep both their theta E and QT values fixed. And so the picture is now this type of picture. So I have my surface of constant theta E as before, but now I need to bring in a surface of constant QT. And it's their intersection where their theta E and QT values would stay fixed for this ring of particles for all times, because these are conserved material invariants as we propagate around in the fluid in this case. And so this was work with Leslie Smith and with a PhD student, Parvati Kulas. And so you do indeed get a particle relabeling symmetry. It's a little more restrictive now. You can't draw any curve you want on the surface of constant theta E. You can only consider curves of constant QT on the surface of constant theta E. And so those are the curves for which the circulation theorem holds. And then you want to take the next step and say, okay, what does this mean for PV? And because there's surfaces of constant theta E, it is indeed true that the appropriate, or one of the appropriate PVs can be defined with grad theta E, but it's not pointwise PV conservation. And so this is where things are quite different from the dry case. So if you work through Stokes' theorem and try to get to PV, what you discover is that it's PV integrated over certain volumes that are conserved. And they're shaped like little pancakes, or they could be bigger if you stack some pancakes up. And so the volumes that you can consider, they have to be bounded on their sides by constant theta E or constant QT. And so in the simplest case, they kind of look like little cylinders or pancakes. And it's the PV integrated over such a volume and moving with the fluid that is conserved in the case with clouds. And there's more complicated details of this too, but this is kind of the simplest version that relates to all the particle relabeling really nicely. And so we thought about some other details and extensions of this. So, question. Why is it obvious that QT curves are closed on theta E surfaces? Yeah, it's not. They might not be. So you could say that for each closed QT curve on a theta E surface, you will have a circulation theorem for that curve. If the curve is not closed, then I don't think you would be able to have a circulation theorem for such a curve. So for instance, what if the QT curve smashes into the surface of the Earth or something like that? Yeah, then you wouldn't be able to have it, and you wouldn't be able to have a particle relabeling there either. So I didn't talk about this, but the particle relabelings now, they are uniform shifts on these curves, because it has to be an incompressible particle relabeling also. And so you can't have a uniform shift as a particle relabeling if your curve goes into a wall, because you can't relabel your particles going all the way. So yeah, very good question. And I need to wait for this little menu bar to go out of the way. Okay. So I didn't talk at all about the details of this. So it all looks easy after you know the answer. So what we did in this paper is we walked through all the details of the variational calculus of Noether's theorem and the Booth-Ness case. And this work is submitted. And the first words of it are Hamilton's principle. And then you can prove all these theorems, though, of conservation just by direct calculation, just starting from the evolution equations. But in order to do that, you have to know what to look for first. And so we did all this work, and now that you know what to look for, you can see it just with direct calculation. Another interesting surprise is that all of these theorems, like the the circulation theorem, and the PV integrated over pancakes, they're also true for the ocean with salinity. So in all that I just described here about the particle relabeling, I didn't mention phase changes at all, really. All I said is that there's two quantities, the equivalent potential temperature and the total water. For the ocean, you could just take potential temperature and salinity as your two quantities that you have. And so all the same calculations follow through for an ocean with salinity. And we work through, or we mention that case, and we do this in the compressible case in this paper, which is it appeared online in Geophysical Research Letters. Another question: do the discontinuities persist in the ocean? Yeah, so in the ocean, I don't think you would have those discontinuities. I think you would have a continuous definition of the energy, but the key thing is just that it depends on entropy and salinity instead of just entropy for a freshwater ocean. So yeah, it's for this particular result in the talk related to PV, it actually, the interface wasn't really a key player. It's just having additional variables in your system. And so this is a brand new result, it just appeared online, so we haven't gotten into too many things with it, but you could try to use these ideas to analyze data. There's also an interesting open question related to numerical methods then. So people sometimes design numerical methods so that they conserve things at a discrete level, like dry PV. So now you could ask, well, what if I try to design a numerical method? Can it preserve these types of integrated PV quantities at a discrete level? It could be a hard question, but it'd be interesting to try. Okay, so that's the second part, the part on PV, and that brings us now to the third topic, and it's the quasi-geostrophic limit. And it's not totally disjoint, it actually brings in PV again, and it brings in the other types of PV concepts like PV inversion and balance. A question before I get too far. At a first glance, it doesn't look like the stochastic flux terms introduced by Landau and Lifshitz to account for microscopic fluctuations would change the basic structure of your results. However, they do represent multiplicative noise, and the diffusion terms would be different in different phases. Are you looking at this? I have not looked at that at all. That sounds interesting. I haven't thought about that perspective at all, but yeah, it'd be interesting to think about that or talk about it with you later, Cecile. That's interesting. Yes. Okay. So next up, this QG limit. Okay, and so the QG equations, which you're probably mostly familiar with, this is a really interesting singular limit, and it has this. It's just a remarkable property of atmospheric dynamics that it's a slow-fast system, even the nonlinear dynamics, and the slow component obeys the QG equation. And we have good understanding of this, relatively good. In the case of dry dynamics, the original derivations by Charney, some rigorous proofs by Embiid and Maida, and this is just to mention a couple of pieces of our understanding of this, but there's much more. On the other hand, for the moist case, I would argue there's a lot less understanding. There's work out there to try to understand this, but I feel like there's big questions, even questions like what are the PVs that describe the QG limit when you have moisture or clouds. Okay, and so before getting into the cloudy case, I want to just review the dry case briefly because I think it'll make the cloudy presentation much easier and faster. Okay, so in the dry case, and again, I'll present this for the Booz and S case since it's the easiest case to think about. I have my momentum equations. I put rotation in here. Now, I guess you could have had this rotation term in some of the earlier parts of the talk, but I just had left it out for simplicity. And so this is the dry case, so just potential temperature and no source terms. The parameters and material derivatives, 3D. And to get to Booz and Esk equations, we have to introduce non-dimensional parameters, Rossby number, Froude number, things like this. I'm just going to call them all epsilon to move quickly. And so rotation is fast, stratification is strong. And so we have 1 over epsilons there, and also in the buoyancy and pressure gradient. And physically, this is, like I was just saying, rapid rotation, strong stratification. Or another perspective is that the inertia gravity waves propagate fast. This is the slow fast part of it. Okay, and there's an abstract version of this, which I think is helpful, so I don't have to keep writing tons of equations all the time. So I can create a state vector that I'll call bold V by putting together the velocity and potential temperature. And then this system takes this form. So it has a linear operator from rotation and stratification, and et cetera, that's fast with 1 over epsilon. And then there's a bilinear or quadratic nonlinear operator from advection. And to then think about the singular limit, we're just doing an expansion as epsilon goes to 0. And so to leading order, everything is in balance from the linear operator. And this is what leads to an elliptic PDE. And then at next order, the DDT terms come in, the advection come in, and things like this. And so if, just walking through this quickly, so you're going to get DDTs and you're going to get dynamics. And what you end up with is an evolution equation for potential vorticity, where the potential vorticity is defined in this way in terms of the stream function in the QG case, and we recover the horizontal velocity from that stream function, which advects the PV. And I think people here are familiar with PV, but if not, then this is also very similar to 2D incompressible Euler, where this potential vorticity plays the role of vorticity from Euler. And this is a large scale limit. So just to describe that with some pictures quick, this is a snapshot of pressure contours, and you can see that the velocity vectors are roughly aligned with the pressure contours. And so that comes from this relationship of geostrophic balance. And this is all on large scales. So this is a plot of energy or variance in different modes as a function of wave number. So the red is the rotational or vortical mode, and so you see that most of the energy is in that mode, whereas the inertia gravity waves have little variance or energy on these largest scales. And so this is another way to think about quasi-geostrophic equations, is that these inertia gravity waves are smaller amplitude or filtered out on these large scales. Okay, so now how does all this work if you have clouds? And so we're back to this system of equations again, where you could write it this way in terms of vapor and liquid with condensation on the right-hand side. And you could try to think, how can I do the QG limit now? And it's hard to do it from this perspective, because now these abstract system, it would have some source terms on the right-hand side, and I would have to think, how am I supposed to take this limit as epsilon goes to 0 with these complicated source terms? And I feel like this is what makes this, writing the equations in this way is what makes it hard. And so this has been kind of the previous treatments of QG systems, is to put source terms on the right-hand side, add a water variable, and think about it this way, like the water is a supplement to the dry dynamics. And this is good, it's useful, because it's a good physical way of thinking about it, that the moisture creates latent heating, and that heats the system and drives the circulation. But I feel like it makes things complicated if you want to, for instance, take the QG limit. And so our question was, how can we try to think about this moist system in more of a unified way, so it looks more like the dry system? And again, it's going to be to use these conserved variables. So this is another version of the equations I'd written down earlier, now with the conserved variables theta, E, and QT. And so now where the clouds and phase changes appear is in the buoyancy, and it's in these heavy sides. So when I now want to look at this abstract form of the equations, now with clouds, and I go to the moist case, this is the way things look if I write it in terms of conserved variables. It's still roughly the same format. It's just that I have to choose my linear operator differently, depending on which phase I'm in. And so I have these Heavisides that tell me how to choose my linear operator. So just going back, that's basically telling me this linear term here, is it this form or is it this form over here for the other phase? Okay, and so what that's going to lead to is instead of having a linear operator, I now have a piecewise linear operator in the case with clouds. Okay, and so now to try to proceed with the singular limit, we can do the asymptotics. I just have to have this piecewise linear operator in it. And I'm not going to walk through the calculation. It's actually not a whole lot different then after you take this viewpoint. And what you get an elliptic PDE, but now it's a piecewise linear elliptic PDE. And so this is normally where like there'd be like an f squared over n squared with rotation rate and buoyancy frequency. And so now you get a different coefficient. I just call them constant u and constant s here for simplicity, depending on which phase you're in, because the buoyancy frequencies are different in the two phases. And you get not only an evolution equation for PV, but you get a second evolution equation. And it's an evolution equation for this m variable. And I've written the m variable in a different way now than I was writing it earlier. They're basically the same. And the reason we call it m is because it's a moist variable, and this is writing it this way kind of indicates that pretty clearly. And this was work with Leslie Smith. And so comparing it to the dry case, these are probably the two main pieces, that there's now a piecewise linear elliptic PDE, and you need another variable. And I'm trying to think, is this going to come up later in the talk? I'll say it now. So the reason you need another slow variable is because when you add moisture, you've added new equations, you've added more state variables. So there's more eigenmodes. And so you have to ask the question, are my new eigenmodes slow or fast eigenmodes? If there's no precipitation, then they are slow. And so you need, to describe the quasi-geostrophic equations, you now need more variables because you need to describe all of the slow and balanced modes of your system. Even if you have precipitation, depending on how fast it is, you could also possibly end up with another slow variable here as well. Okay, so next I want to just say a little bit more about those two pieces, this elliptic PDE and this slow variable. So this is a slight variation of it with specific values of 1/2 and 1 for these coefficients. And so what's different is that now you're given not just PV, but you have to be given PV and M. And then from those, you find this unknown solution psi. And the non-smoothness of this is kind of clear because there's these Heavisides that I'm emphasizing. But what's also interesting is this is a nonlinear equation because the Heavisides are determined by the water, QT. But a priori, you don't know the water. You only know PV and M. And so you can now write the water in terms of this M variable and the stream function. And so really, I'm always hiding it up here in these Heavisides. These Heavisides actually depend on the stream function itself. And so this is a nonlinear elliptic PDE. And so you don't even know the cloud boundary when you start to solve it. You discover where the cloud edge is after you find the solution psi. So it's a really cool new PDE. And then the second new piece is this new slow variable M. And so I just wanted to mention this version of it, of its definition. So you could write these moist QG equations in terms of a vorticity evolution and theta E and QT evolution. And the way to see M arise is from trying to eliminate W. So you've maybe derived the PV evolution equation before, where you try to eliminate W, say, between this W here and the W in the vorticity equation. There's another way to eliminate W, which is even easier by taking a linear combo of the QT and theta E equations. And so that's where our definition of M comes from a linear combination of QT and theta E. And just to demonstrate that it is truly slow, this is the results from some 3D numerical simulations where, and I'm showing a 2D slice through it. And so this is at time 0, 0.1, and 0.2, and epsilon is 0.1 in these simulations. And so the gravity wave timescale is 0.1. So I'm showing evolution on the gravity wave fast time scale. And what you see is that this PV quantity barely changes at all because it's a slow quantity. And same with M. M barely changes at all on this fast wave time scale because it also is a second slow quantity of the system. Okay, and so the final piece I want to talk about are these other PV concepts of inversion and balance. And I think there's a really interesting piece that comes up now when we think about these with moisture. Now I got this menu in the way again. Okay, now it's gone. Okay, so I'll show some results from some numerical simulations. We've done simulations of a variety of different types of systems to try to think about these ideas. And so if I had to pick one piece, I think it would be this piece of it that I think is most interesting. It's that moisture has both balanced and unbalanced components. And I have not seen this mentioned previously, and I think you can now start to see it when you have PV and M inversion to start to think about it more clearly. And so to give a little bit of background on this, in the dry case, if you want to do the slow fast decomposition, then you go to PV inversion. So you solve this elliptic PDE, and that will give you the slow or balanced part of the system. And this is well known in the dry case. You have your slow PV quantity and you find your stream function, and you go from there. Okay, so then the question is, what do you do in the moist case? And the conventional wisdom has been that you can't do it. You can't do PV inversion if you have phase changes. So people would often write a PV in terms of theta E, and these are just some quotes from some papers, saying that, this is not invertible. The invertibility principle, it's not applicable when you have this moist PV. And so this is all correct. So what was missing is the M piece. You can't do PV inversion by itself because moist systems have a second balanced component. So the PV by itself is not enough information to obtain the balanced part of the system with a moist system. So if you have PV and M though, then you can do PV and M inversion. And we've started to look at this a little bit in a few papers with WRF simulations and also some Booz-Nesk simulations too. So just to show this a little bit, does water really have balanced and unbalanced components? This is an example simulation, 3D moist Booz-Nesk equations. I'm plotting the signal of the total water, and that again at 3 times. So this is like the gravity wave time scale of 0.1, 0.2. And you'll see that this total, so the initial condition is just a blob of moisture on top of a background turbulent state, including vortical mode and waves altogether. And you'll see that the total water does change substantially on these timescales, and that's because there's waves in the system. But I can do a separation. I can identify the balanced part of the moisture, and you'll see that it hardly changes at all. Many of these little striations are identical from one of these times to another. And again, I didn't use like some kind of time averaging to define this. This comes from solving the elliptic PDE, given the data at one time step, to isolate the balanced part, just like in the usual dry case, but now with PV and M inversion. And I can also then separate the unbalanced part, which you can see does substantially change from one time to another due to these fast gravity waves. Okay, and so to summarize it all, this is one collection of work toward adding clouds to fundamentals of GFD, and the 3 main pieces that we've been working with are defining a piecewise quadratic energy, conservation laws for potential vorticity, and then the quasi-geostrophic limit. And I guess some of the main themes that have come up are writing the equations in piecewise form using Heaviside functions, which also means using conserved variables. And it kind of unifies things rather than having these source terms on the right-hand side that I view as like a source term with the dry equations. And this M variable, which keeps coming up in many parts of this, which is related to an additional moist eigenmode in the system. And then finally, this idea that moisture has both balanced and unbalanced components. I feel like that's one of the most interesting new pieces that came up through all this. So thank you very much for your attention.
Thanks a lot, Sam. This is really a very great talk. So do we have more questions for Sam? So I have a very naive question for you, Sam. So here you need to define the so you have this heaviside function that distinguish between places where you have saturated water and non-saturated water. So at which scale are you making this description? Because if I look at a cloud, I mean, it is saturated at a scale, basically the scale of a drop. And so I guess this is not what you mean to describe when you will do a numerical simulation.
That's right. Yeah. So in any simulation, we're going to have some type of dissipation present, whether it's like Smagorinsky or something like that for a cloud resolving model or large eddy simulation, or we use hyperviscosity if we're doing like a triply periodic box. Yeah. So I guess in a lot of these scenarios, we're using inviscid ideas with the assumption that the data is sufficiently smooth for us to think about these things, even though in nature or in simulations, there's going to be smaller scale things. Yeah, and I guess we view this as being sort of the extension of dry GFD ideas. But I guess it's more of a problem now with clouds, like you're saying, because there's perhaps even more small scales appearing when you start to think about cloud edge.
So if you have small scales and droplets and so on and so forth, so wouldn't it be relevant to describe just the fraction of saturated water rather than directly 0 or 1, whether it is saturated or not?
Yeah, I'm trying to think about other, like I'm just trying to think about large eddy simulations, for instance, and trying to think what type of microphysics would I define in order to do that. I guess you could use like a bin microphysics type of approach with like a kinetic theory type of equation to count how many droplets I have. I don't know if that's precisely what you were having in mind.
No, I have nothing precise in mind. It's very just
yeah. I mean, to some extent, yeah, I guess to some extent that would get to when does the continuum approximation even break down? Because I mean, even with the 0 or 1, you can have very low concentrations of liquid water, and it's counted as being above saturation. So really, I guess if I'm understanding right, you'd be asking about. And I guess right now those would be cases of very low liquid water concentration, or whether they're being approximated as 0. And yeah, I'm not sure. I guess it would, if I were going to try to write the equations down, I'd have to think about a different system, I think. That'd be interesting to see how much of this carries over to that. I see 2 new questions, maybe. Cecile, I'm afraid I missed one thing. Is the unbalanced part fast? Yes, sorry. Unbalanced means fast, basically. Yep. Fast, slow, balanced, unbalanced, vortical versus wave. Yeah. And Colin Cotter asked, what about a semi-geostrophic limit? Yeah, we thought about that a little bit. We haven't worked it out at all ourselves to see. But yeah, that'd be interesting for thinking about fronts and things like that. But yeah, I don't know. You would think that you could do something similar in that case. And yeah, Cecile, you want to follow? Oh, and you're right here. Yeah, I see you're on the video now.
Okay, I was just wondering though, if it's a fast thing, could you use homogenization to add a stochastic term to take into account the unbalanced part? And that might actually address Freddie's question too.
Yeah, that would be interesting. So would you? I guess you would maybe have to replace the fast evolution equation by a stochastic version, or
Yes.
or just add a stochastic component to it. Yeah, then
No,
you could probably do
you don't just
homogenization.
add it. You can't just add it. You have to conserve things. So, I mean, you know,
Sure.
the question is whether or not you could have a fast equation and a slow equation, and then use the homogenization to put the representation of the fast one into the slow one as a stochastic term.
Mm-hmm. Yeah, I think that'd be really interesting. And to tie that to some real physical observational type of question. One idea I see out there is the idea of an effective stratification or effective gradient, because you know there's these different buoyancy frequencies, for instance, in 2 different phases. And so one question would be, it's kind of useful to be able to think about just one of them, and it's effective in the sense that it's kind of averaged over between the 2, depending on how cloudy or not cloudy you are. And so this would possibly be one way to rigorously get to, you could wonder, is there a system that looks like the dry equation, or even closer towards like the dry equations, with an effective buoyancy frequency, for instance? And yeah, that would be just thinking about this. Besides, what would I apply this to? That's just one thought of where that might go. That's interesting.
Thank you.
Yeah, thanks, Cecile.
Okay, thanks a lot, Sam. This was really a great talk, very fundamental things.
Thank you very much for having me. And thanks a lot for all your